Good evening, and welcome to another of our Planning for 2023 Specialist Mathematics webinar, Logistics Differential Equation. Our presenter tonight is Bojana Graham.
Hello.
Hi, Bojana. Nice to have you tonight.
Hi, Daisy. Hi, everyone.
There will be definitely an opportunity to ask Bojana questions at the end of the session via our chat function. So let's not delay any further. I'll hand over to Bojana now. Enjoy the session.
Good evening, everyone. So what we'll have a look today is the logistic differential equation, which is sort of new on the syllabus of the new specialist mathematics courses. Of course, this will be in units 3 and 4 when we learn about differential equations. We already have the separable differential equations, so this is not that much. We separate variables and we use partial fractions. So this part is sort of the same, but we didn't look exactly at the logistic curve as per se, and we don't even know that much how much will be on the exam and how much there is. But there is definitely a scope for lots of investigations looking at the logistic differential equation and the logistic curve. So we'll have a look at some real data, real life data, how it can model the logistic curve, and then we'll look how the parameters change the shape of the logistic curve, and also what is the greatest rate of change. I will start with some historical notes. So the logistic model and logistic differential equation was first proposed by the Belgian mathematician Verhelst in 1838. So his differential equation was the rate of change of the population is proportional to two factors, to the population itself and to this other factor, which is 1 minus P on K. These were the pronumerals used by Verhelst, but of course those pronumerals can vary. So if we look at the data which was available to Verhelst, it was years 1790 to 1840, and he tried to model the population using this data. So let's try to see how it will work, if I can get out of this, sorry. So what I have done here, I have entered the data just to save some time. So I have years here, but also we can enter the data from 0 to whatever number we have, only really 5 values, so not that many, and the population, which is in millions. So we'll try now to get the curve. So we need to get our purple graph, and I will use time rather than year, and I will use the population. So as we can see, it doesn't really have this characteristic S shape yet, but let's try to find the regression. So we go analyze regression, and we scroll down, we can see show logistic D equals 0. So when we do this, we can see this is the typical logistic equation with the Euler's number then. So let's see what happens if we actually try to change the data a bit and extend the time and extend the values. So it starts getting this logistic shape. So as we can see, that was the data available to Verhelst in those days, but we can now clearly see the S shape happening now. Now, if we now go and have a look at the actual data, which is from the US Census data for the total population. Again, these are some ideas for the investigations, for the students getting some real data and trying to model it with the logistic curve. So if we look at this data, I also entered the data on the calculator and we can compare those two curves. The equations are slightly different, but apparently the modeling was pretty close, and Wellhurst wasn't, if we look at 1940 data, it was about 1% error only in using this logistic data. We can also find the point of inflection if we use the calculator screen and get our regression line as a function, but we'll get to this a bit later. The other idea from real life situation is looking at iPhone sales. So I've collected this data here from 2007 to 2017. Again, we have sales in millions. So if we go to the calculator and look at the data, I just closed that. So we have iPhone sales data. Again, I entered them. This time I put just time in years and the phones. And we do the same. We can get our purple graph. And if we go time here and phones, now we can see that the curve has a bit more as shape. There is one point which is a bit off. So it could be a good discussion looking which year it was and why would this point be off. And similarly, we can use regression, and we again using logistic with D0, and we get our equation. So these are the sales, original sales from this data 2007 to 2017. And we have this characteristic S shape, which is quite interesting. And then we can look at the data for the following years, 2018 to 2021, and trying to predict using our curve how close the numbers are to the actual data. And of course, it won't be exactly close, but there is again some scope for a good investigation here looking at this data. So if I go again to the calculator, this is the iPhone sales data with all the sales. As I said, we can perform the logistic regression in the calculator screen. The advantage is that the equation gets saved and then we can actually draw it. This time I drew it using the scatter plot. So there is another option which allows us to actually sketch the curve, which we already found, and showing how it fits the points. So there is lots of options using different graph entry and seeing what happens. And if we again use the function entry, we can find the points of inflection by using analyze graph and number 5 inflection point. And then, of course, there is a discussion, what does this inflection point tell us about the growth rate of the Apple phone sales? So this is predicting. Now, if we look at another way, looking at the logistic curve, the other way of doing that is using the slope field. So if we have this equation and have the point. So we might try to do this on a calculator, also obtain the logistic curve. So I might do this live. So we get graphs, and we need graph entry. We need the differential equation. So y1 dashed equals 0.01 y1, because it has to be in terms of y1, and we go times 100 minus y1 again, and we had the 0.5 and 40, and of course we won't see that much here, so we will need to change our scale a bit. So that's a bit of playing with the scale, not quite enough, and so on. And now we can see a nice, again, shape of our logistic curve, and this point looks like initial condition is nearly the point of inflection here. So this is another way of obtaining the logistic curve by using the slope fields and following the slope fields, having this shape when we have the equation again, which has the proportional scale factor, and it's proportional to y variable times, and there is this other bracket when we have the difference. So that's what the differential logistic equation is, and it can be, of course, also obtained by drawing the solution curve on the slope field. So that's what we've got here. And I might just get off here. So there is a good, again, scope for the discussion of the students. So what does that mean, this shape of the curve? What's happening? What are the parts of this shape? And so on. I even drew here the horizontal asymptote, but we'll get to this in a second. So basically, many populations would grow exponentially at first, but then because of the limited resources of land, food, predators, as we see, this S shape occurs because the rate of growth slows down after the point of inflection. So the logistic model can be used to describe the number of people infected by a virus. So possibility, again, collecting data for COVID before vaccination, after vaccination, and seeing what happens. There are some chemical reactions which also follow the logistic curve. And of course, the main one is population growth with birth rate and carrying capacity, which is this limited value for any population. So let's use this type of the differential equation. I mean those pronumerals. The rate of the change of population with respect to time is proportional to two factors. It's proportional to the population at any time, and is proportional to 1 minus P over F, where F is this carrying capacity. So the first factor controls the exponential nature of the growth when P is small. When P is small, this is the main factor affecting the shape of the curve. But when P is approaching F, of course, the growth, as we see on the S logistic curve, slows down, and this factor actually ensures that the growth approaches zero as the population approaches the carrying capacity. So to solve the logistic equation, of course, we use separation of variables and partial fractions, but for tonight, we'll just do it on CAS. So again, we'll look at this upper limit. So what we'll do now, we'll try to see how the parameter K will affect our logistic growth and how this shape will change. So we'll try to solve the equation on, as we say here, on the on CAS, and then we'll sketch the value, we'll sketch the logistic curve for various values of K. I just get the equation ready to enter. So let's go to the calculator. Again, I close this one because we've done this. And this is the slope field as well. So I open a new document just to do it live, and I will get the calculator. So let's solve the differential equation. So we go differential equation solver. So we go P dashed. I believe most of teachers would know how to enter this equation, equals, and I will start with 1.4, and then we go times P, and then we go time 1 minus P over, and we'll, for comparing how K affects the graph, we'll use the carrying capacity 800. So we have P dashed is 1.4 P times 1 minus P over 800. Independent variable is time, dependent variable is P, and let's say we say that P, not capital, sorry, P in 0 equals 10. So if I do this, I get this equation, and now if I go up and bring it down, I can say P in T, and I will have the calculator remembering that's my P in T, and that's done. So if I assigned P in T to be this equation, now I can actually sketch it, going P in X, and of course that will not look very good, so let's use zoom fit and change that to -1. And now this is our curve when K was 1.4. Now what we can do, we can repeat the process quite quickly by entering this and changing it to 1.6. So we have this equation, and again, I can say this will be my P1 in P, and I will assign it, enter. And now if I go to the calculator, I can say P1 in X, and I will get my logistic curve for the value 1.6. Let's try one more, but you are getting the picture. So we used 1.4, 1.6. Let's try 1.2. And again, I will say that this will be P3 in P, and we have to change equals to a sign. And that's my P3, and I will add this to the graph, P3 in X. So we can clearly see now what is happening when we change the K value, which is sort of birth rate. And interestingly, if we now go analyze graph inflection, so let's do inflection for this graph, do inflection for the blue graph, and we'll do inflection point for the red graph. So there is something interesting happening for those points. So we see 400, 400, 400, but of course the time after which the point of inflection occurs changes. And that's again a good investigation for the students to see what happens when we change the birth rate. Similarly, we can repeat all that by varying our F values. So here we varied K values, looking at various curves and the point of inflection. So investigation ideas are how is the location on the inflection point, if there is one related to the carrying capacity, record your conjecture to later prove it algebraically. What is the significance of the inflection point in terms of the population growth rate? For specific values of K, F, and P0, plot the direction field and your solution function to verify visually that you solve the differential equation correctly and so on. So these are just some of the ideas. So we vary K, and we can also vary F. So of course, carrying capacity is our horizontal asymptote. But interesting thing here, if we vary F, what happens to the population? What's the population when we have the maximum growth, which clearly we can see it's half. I don't have the numbers here, but it is half compared to when we had a constant value of the carrying capacity. Then in the varying K, we can see that the P value here is 400. So there is a lot happening in the logistic differential equation, which can be investigated. Another way of looking at this is also using, I'll close this because we finished, and I close this. And another thing, we can do it once we solved our equation in general, we can create the notes page. So we write our general solution to the differential equation, and we vary the constant of F, P0, and K. So let's say I had it 500, but sorry, if I change this to 600, so I can see straight away what happens to the graph. And well, something didn't quite happen here because that wasn't the note page, but there are some ideas when we can look it up, and then we can change to 1.4 and so on, and we can see how our parameters change. Another way also of doing it is looking at sliders. So this time I have my solution to the logistic curve, and I set up 3 sliders. One is for the initial population, one is for the carrying capacity, and one is changing K. So that is quite good because it's quite dynamic. We can see if I can change what happens to the inflection point, and similarly what happens to the shape of the curve and to the inflection point. If I change F, P doesn't matter that much, but of course it will also have an effect on the inflection point. So as I said, there is a lot to investigate for the students.
At this stage, Jana, we don't have any questions, just a couple of comments which are quite positive with regards to the demonstrations you're showing. Appreciate your time today, Bojana, and I appreciate the audience for watching today. In the next few days, you'll receive an email containing a link to the recording of tonight's session so you can review at your own pace, along with Bojana's files and a link to your PD certificate. Once again, we thank you for attending, and what you can see at the moment is the schedule of the upcoming series, webinars that are part of this series. So the next one relating to specialist maths will be on the 11th of October. We hope to see you there. Have a lovely evening, and thank you very much again.
Thank you.